Hello, in this video we are going to understand the basics of optimization. Okay, so the main problem here is to understand what optimization is, and here on this slide you see a very basic definition of optimization. It says that optimization is the process of selecting values of decision variables that maximize or minimize an objective function. Okay, so there are two or three critical elements given in this definition. The first one is decision variables, and the second one is the objective function. So maximize and minimize, these are mathematical concepts that are usually used for functions. So objective function is our purpose function. What are we trying to do? What's our objective? What's our aim? So in each model that we are going to put together, we have to answer this question. Okay, and decision variables, those are the variables that we can control to make that a system a lot more efficient or better. So basically, if you go back to this definition, it says the process of selecting values of decision variables. What are the best decisions out there so that we can make in order to maximize or minimize our objective function? Our objective function is a utility function, or it might be called as a desire function, right? So if it is a profit, if it's a good thing, we would like to maximize it. If it is a negative thing, like cost or time spent, right, we would like to minimize that, right? So based on our objective, we can select either minimize or maximize our desires. Okay, after we do that, we hopefully will achieve optimal solution. So optimal solution is the best set of decision variables, the best decisions that are out there in order to make our objective function the best, very best. Okay, there are three important concepts on this slide. The first one is decision variables, the ones that we can control. The second one is to set up our right objective function. And then finally, the third one is to figure out what optimal solution is. Okay. All right. So now another term comes into way. It says constraint optimization. So there is this optimization term here, still valid, but we do also have some constraints that we have to worry about, right? So the constraints are the limitations or requirements that decision variables must satisfy. Okay, so I would like to achieve that objective function, let's say maximizing the profit, but I have limited amount of, let's say, workers available. I cannot have infinite number of workers working for me, right? So that's a constraint. There might be several of those constraints. For example, the first one is the amount of material used to produce a set of products that cannot exceed the available amount of 850 square feet. So this is a space constraint, right? Or maybe another constraint can be the amount of money spent on research and development projects cannot exceed the assigned budget of $300,000. Okay, there might be several other constraints. That's good. So, but the question arises: so how do we convert them into mathematics, right? So eventually we will have to deal with the math at the end. So we have to know how these constraints are related to the decision variables that we are going to define, and hopefully the impact of those decision variables on these constraints, and also the objective function. So we have to figure out the way to transform all these verbally defined constraints into math. Okay, let's go over it step by step. For example, the first one specifies a space constraint, right? So we have to have set of decision variables that can control the amount of material used. Therefore, we can make this constraint possible. We can say that, okay, on the left-hand side, this is called left-hand side, and this side called right-hand side. Left-hand side of this symbol right there, and then right-hand side of this symbol right there in the middle, right? So that we can define 850 square feet as a constraint of ours, right? So the second constraint was about the money, the total money availability. On this one, we have to specify the amount of research and development on the left-hand side as a function, so that we can say, okay, this is less than or equal to 300,000. Finally, the third one is the number of units product produced, it should be greater than or equal to 500. I think that's what it was saying verbally. Yeah, it says that the contractual requirements specify that at least 500 units of product must be produced. The fifth one is a mixture of fertilizer must contain exactly 30% of nitrogen. So we have to have a controllable variable that says amount of nitrogen in mixture that has to be specifically exactly equal to 30%. Finally, the last constraint says we cannot produce a negative amount of a product. This is also called a non-negativity constraint. If we do have a decision variable, we can say that, okay, make this always greater than or equal to 0. The left-hand sides are called constraint functions. So long story short, we have to figure out a way to put a function on these left-hand sides. Okay? The rest is easy. The rest is to come up with the right symbol and then come up with the right-hand side values. Okay, how do we do it? Suppose that the material, for this is a different example, suppose that the material requirements for 3 products are 3, 3.5, 2.3 square feet per unit. And then we say let A, B, C represent the number of units of each product to produce. Okay, these are our decision variables. Okay, A, B, and C. It represents the number of units of each product to produce. Therefore, the amount of material used to produce A units of product is going to be A, right? It has to be 3, 3.5, and then 2.3, right? Those are the requirements. So then we can control the amount of material used to produce A units of product A, right? So it is just basically 3 times A. Okay, so the amount of material used to produce B in this way, if you repeat what we just did for A, it's just going to be 3.5 times B, right? And then finally for C, it is just going to be 2.3 times C. So if you add them up, the left-hand side inverts, it's going to tell us the total material used, right? It is less than or equal to 850. Okay, so by this way, this is the function that controls our amount of material used, and then we can say, okay, this is less than or equal to 850. This is how we convert constraints inverts into functions, constraint functions. There are several definitions for the linear programming solutions. So feasible solution is the one that satisfies all the constraints. So you don't need to worry about the objective function here. You just look at all the constraints. If all the constraints like these ones are satisfied, meaning that those are not violated, right? So then you got a feasible solution. Again, if you are looking for a feasible solution, you don't have to worry about your objective function. Your objective function can be really, really bad or can be really, really good, but we don't care. We are looking for the feasible solution, then you check the constraints. Well, if the problem has no feasible solution, if there is no way a solution that can satisfy all the constraints, then you claim that your solution is infeasible. It means that there is no way you can satisfy all the constraints. Again, we don't care about the objective function value because our first objective is to find a feasible solution so that we can make it better. Then a problem that possesses the best solution is called the optimal solution. Okay, the optimal solution must be a feasible solution. Okay, the first rule of having an optimal solution is that that solution has to be a feasible solution. Otherwise, an infeasible solution cannot be an optimal solution because an infeasible solution is not really a feasible solution at all. Okay, so an optimal solution is a feasible solution. Well, another question is, a feasible solution always be an optimal solution? Not necessarily, right? We might have infinitely many feasible solutions, but all of them may not be the optimal solutions. Well, we might have a case where we have a single optimal solution or alternative optimal solution, and we are going to study them later on. Okay.